Okay, so I'd like to welcome you all to another edition of Quantum Computation and Isolation. So today I'm very happy to introduce Jessica Lemieux from University of Sherbrooke. Jessica got her bachelor's degree in physics and mathematics from the University of Ottawa in 2015. She got a master's degree from the University of Sherbrooke in 2018, and she's currently a PhD candidate at the University of Sherbrooke 2018 to present. Starting in 2018, she was a research intern at Microsoft Quantum, and from 2020 to present, she's been a scientist at 1QBit at the Hardware Innovation Lab. And today she'll be talking about resource estimate for quantum many-body ground state preparation on a quantum computer. So please help me in welcoming either by muting yourselves and clapping or by just clapping virtually, Jessica Lemieux.
Thank you. So could you just confirm that you can still see my slides?
Yes, I can see your slides and I can see your mouse.
Perfect. Thank you. So thank you for the introduction, and also thank you for the invitation. So as you already said, I'm a PhD student at a University of Sherbrooke in Institut Quantique, and I'm also a scientist for 1QBit. My name is Jessica Lemieux, and I'm going to present some work I've done during my PhD, my early PhD years at the University of Sherbrooke, which is resource estimate for quantum many-body ground state preparation on a quantum computer. So this work has been done in collaboration with people from Sherbrooke, so Guillaume Duclos-Cianci, David Sénéchal, and David Poulain. You can find the paper related to this work on the archive for now, if you're interested in more details. So it has been well known for a few decades now that a quantum computer could efficiently simulate the dynamics of a quantum system. So it has been studied in the past decades, and actually first introduced by Feynman with this idea that a quantum system should be more a natural way to simulate the dynamics of a quantum system. Oh, and by the way, if you have any question during the talks, please feel free to interrupt. I may not see your virtual hand, so just speak up. So as I said, we wanna simulate the dynamics of a quantum system on a quantum computer, and one way to achieve such a task is to first initialize the quantum computer in a state of interest, maybe the ground state of some Hamiltonian. So the dynamics is easy to solve on a quantum computer, but it could also, but initializing the system may be a bit less natural for the quantum system, for a quantum computer, because it will, because we need to solve the static problem. So this eigenvalue problem here. So here I have kind of an abuse of notation in the sense, I just wanted to emphasize that we want to find the kind of the instantaneous ground state of the Hamiltonian. So it's not like a time-dependent Hamiltonian here, but really like a time-independent problem. So classically, we know a bunch of methods to solve this problem and approximately find a solution for the ground state. We can think about density functional theory, quantum Monte Carlo, or tensor network methods. But even if we find classically the solution to this problem, it is not clear how we will we will initialize the quantum computer given the solution. So we need some techniques. So the algorithm to initialize the quantum computer that we're going to talk about today is the discrete adiabatic state preparation. And we wanted to estimate the resource that it will take to actually prepare the ground state of a many-body quantum system on the quantum computer. So to do so, we used classical tools to benchmark the algorithm, but also these classical tools could be helpful to help optimize some parameter for the quantum algorithm. So we can see this also as a classical assistance for the future quantum computer. So for concreteness, we did simulation for the 2D Hubert model. This model This model is a typical model for strongly correlated electrons, and it doesn't have any analytical solution in more than 2 dimensions, in 2 dimensional more actually. So it's a problem that is kind of hard and that has some interesting features. So just to understand a bit what this model is about, so it's kind of so it described kind of a simple version of an atom on a lattice, where at each vertex you have an atom, a site where you can have either a no electron or a spin up, a spin down, or a spin up and down. So you have 4 possible states at each site, and it's kind of a simpler description of the oneness orbital. So you have the first term of the Hamiltonian that describes, it's the upping term, so kind of the kinetic energy, where it describes like the possibility of having an electron that goes to one side to a neighbor side. The neighbor are defined by the edges that you can see on the lattice. The second term is kind of a simpler version of the Coulomb interaction. So it's a potential interaction that is simpler in the sense that it defines repulsion on the same site only. So it actually just counts the number of double occupancy. So it's a repulsion on the same site only, if I may say. In this model, what parameter that is kind of important, it's the ratio between U and T. Because when you have only like one part of this Hamiltonian, it's kind of easier to solve. But when you have a competition between the 2 parts of the Hamiltonian, it makes it harder. So as mentioned, we want to prepare the ground state of the U-bar model on a quantum computer using the discrete adiabatic state preparation algorithm. So to introduce this algorithm, I want to first talk about the adiabatic state preparation, the continuous version. So the idea is kind of simple. To solve like the static problem that I referred to, where we want to find the ground state of some Hamiltonian that is represented here by HF, we're gonna use an evolution to initialize it on a quantum computer. So we first start by initializing the quantum computer in some ground state of an well-known and easy to prepare Hamiltonian, here noted by HI for H initial. And if we initialize the Hamiltonian in this ground state and have this time-dependent Hamiltonian that link those two initial and final Hamiltonian, and we perform an evolution that is slow enough, we're going to remain in the ground state all along the evolution. And when I say slow enough, I mean slow enough compared to the gap. So typically the adiabatic state preparation, well, from the adiabatic theorem, we know that this algorithm should be upper bounded by 1 over the gap square. And one way to understand this is it kind of characterizes the change in the Hamiltonian. So more change there is in the Hamiltonian, more time you need to kind of let the ground state adapt and evolve along the path. So you ensure that you don't jump off to an excited state. So you remain in the ground state all along. So for our simulation, what we use, so it's kind of a linear interpolation where we first start with the initial Hamiltonian that is only one part of the U-bar model, which is just the kinetic part. So it's easy to solve. We know how to initialize the computer in the ground state of this part, and we slowly turn on the interaction, the potential term. So we slowly turn on this term, and it acts as a linear interpolation. This is just a choice. Actually, you could use any starting Hamiltonian that you want to reach your final Hamiltonian, or any path that you want to link those two Hamiltonian with your time-dependent Hamiltonian. The only thing that you need to ensure is that you have a non-vanishing gap all along your path. And Actually, so here we implemented linear interpolation, but it has been shown that actually using something like a symmetry breaking field could lead to better scaling, better results, because we could have a bigger gap, for example. But this is not exactly what we're studying in this paper. To describe the discrete version of the adiabatic state preparation, I want to first introduce the quantum Zeno effect. So the quantum Zeno effect, if you recall, it's something that kind of helps fix a state in time to avoid decoherence. This is the idea that if you have a state, so here I have a state represented into the block sphere, and if I repeatedly measure it along an axis, I will have a high probability of measuring always the same state because the state won't have time to interact and move and change. So this is the idea of if I repeat some measurement in the same basis, I should always measure with high probability the same state. But the version that the version of the quantum Zeno effect that I want to discuss today is slightly different. So is this idea that, let's say, instead of measuring always in the same basis and keep always the same state, I'm going to mimic an evolution by changing the measurement basis and dragging the state into the direction that I want. So let's say I start in this state here and I want to reach this state there. Well, if I was to just do a measurement along this axis and I started with this state here, well, I will have a probability of succeed that is only 1/2. So it's not that good. But if I had intermediate measurements in between those two measurements, I will increase my probability of succeeding. So let's say if I first start by having a measurement along this axis, I will, with high probability, measure the state that is the closer to my measurement axis. So this one instead of the one in the orthogonal one, the one that will be pointing in the other direction. So I can keep adding some intermediate measurement that are close to one another to drag the state in the direction that I want until I reach the final state that I was interested in. And the overall probability of such a protocol will be higher than 1/2. So the probability of the overall protocol is the multiplication of the probability of succeeding of each individual measurement, and it will be higher than 1/2. So this is kind of the same idea that we want to discuss in the discrete adiabatic state preparation algorithm. So what we're going to do is we're going to drag the ground state of our initial Hamiltonian into the ground state of our final Hamiltonian by adding some intermediate projective measurement. We are going to choose those projective measurement to be decomposition in the eigenbasis of some other intermediate Hamiltonian. So basically, we're choosing Hamiltonian that are on the path defined by this time-dependent Hamiltonian, but we're choosing instantaneous Hamiltonian along this path. So if you are in the ground state of H0 and you choose your next projective measurement to be close enough in the sense that we don't have much change from H0 to H1, you will have a high probability of measuring the ground state of H0 if you start in the ground state of H1. So this is the same idea that you have to go slower, or you have to do more measurement when you have a lot of change from one Hamiltonian to another. So as I mentioned, our goal in this paper was to give a resource estimate for preparing the ground state of a quantum body system on a quantum computer. So To do so, we need to evaluate some quantity. We need to know what is the probability of succeeding of each step. So the probability of measuring the ground state of the Hamiltonian Hg when you are in the ground state of the Hamiltonian J-1. And you also need the gap, because when you want to do a projective measurement and the eigenstates of an Hamiltonian, what you do is an energy measurement. So your energy measurement need to be able to distinguish between the first excited state and the ground state that you're interested in. So if you want to ensure that you're in the ground state, well, your energy measurement must be more precise than the gap. So this is where we use the classical tools to benchmark our algorithm. The other thing is those classical tools can be used to optimize the path that we're going to choose. So the number of intermediate measurement, the number of Hamiltonian that we're going to use. The technique that we use is a tensor network technique. I don't want to go into the details of it, but for the people who are familiar with the technique, so we use MPS, a metric product states, to represent the states of our lattice by snaking around the lattice that way. So each matrix here will represent the site. And then we use DMRG on our MPS to found the ground state. So DMRG is a numerical technique, a variational numerical technique to minimize, to find a minimum of the problem. So this is the basic idea. So we can find the ground state and then its energy. And by a technique that is quite similar, we can find the first excited state to get the gap. So this is how we found the useful quantity with our classical tools. So now I want to discuss a bit more about how do we define this discretization, this path. Where do we know where to put our Hamiltonians in order to have a high probability of succeeding of our algorithm? So there is, you could have some kind of constant time step that you define by 1 over the gap. But here we choose to do something a bit more clever. So we won't have like the most optimal density of measurement, but we may have something that is better than a constant time step. So the idea is we first start by calculating the probability of succeed if we were to perform the algorithm in exactly 1 step. So let's say I start in the ground state of H0 and I try to find the ground state of my final Hamiltonian in exactly 1 step. I will have a probability of succeed that is probably really low, but that algorithm doesn't cost much because I only do 1 projective measurement into the ground state of my final Hamiltonian. So I compute the cost of this version and the probability of succeeding, and then I cut my step in 2 to have now 2 steps, and I compute again the probability of succeeding of each step. So the probability of succeeding of this step here and the step there, and I compute again the overall cost. So now the cost will be higher because I have now 2 projective measurements. But the fidelity of this algorithm is bigger. The probability of succeeding of this algorithm is bigger. And I go on. So let's say the smallest fidelity, the smallest probability of succeeding between those 2 steps was F2. So let's say F2 was smaller than F1. I then cut this step in 2 and compute again the new probability of succeeding of those 2 new steps here and the overall cost of this algorithm. And I go on and on. I always cut in half only the smallest probability of succeeding to be able to increase my overall probability of succeeding by adding not too much steps, not too much cost as my algorithm. So I go on and on. And what you will observe is that you may not have like constant time steps because you may have like a higher density of measurement around here. And typically what we will expect is that we'll have a higher density of measurement where the Hamiltonian has more change in it, and that will typically be where the Hamiltonian has a smaller gap. So when do we know where to stop having time step? Where do we know that we have something that is that will give us a sufficiently high probability of succeeding of our overall algorithm? So this is where we have kind of the classical assistance that that could help us, and it's by finding the minimal time to solution. So the idea of such an algorithm is basically you try to project into the eigen states of your instantaneous Hamiltonian, but if you don't measure, if you don't find the ground state, you collapse in a state that is orthogonal to that one. So you kind of fail your measurement, but you have to restart from scratch. You have to restart from the very beginning of your algorithm. So there is kind of a trade-off between a long protocol that has a high probability of succeeding and a short simulation that has a low probability of succeeding, but you repeat more often. So this is this idea that let's say I have some protocol that has a probability of succeeding and that has a certain amount of step in it. I can repeat it a few times to increase my probability of succeed or the overall probability of failure of this algorithm. So the time to solution is kind of an approximation of it. It's kind of an average of the cost, the total cost, when you take into account the fact that you also have to repeat more or less your algorithm. So here it's really just the expression to give the number of time that you will have to repeat your algorithm in order to reach an overall probability of failure of epsilon. And each time you run this algorithm, you have a cost that is bounded by the cost of your overall algorithm. So you have a formula that looks like this. So if you minimize that formula, you will find the optimal trade-off, as I said, between a simulation that has a high probability of succeeding, but that is costly, but that you need to repeat less often, and a short simulation that has a low probability, but that you will have to repeat many times. So typically, a time to solution graph will look something like this, and you will have a clear minimum that is exactly the trade-off between repetition and costly algorithm. So you have it in terms of the number of steps. What I mean by the number of steps, it's really like the discretization that we use. So the number of intermediate Hamiltonian, so projective measurement that we use. And so we will choose we'll choose this number based on this graph. So this is a classical optimization that we do. Now, there is something that I want to emphasize about this TTS formula. So you may recall that I said that the adiabatic state preparation scales is upper bound. The scaling of the algorithm is upper bounded by 1 over the gap square. And here we have a scaling that has an explicit term in 1 over the gap. So we could be tempted to think that it is faster than the adiabatical schedule, but it's not necessarily the case, because we have some kind of hidden term that depends on the gap in this term here. Because recall that the gap kind of characterized the change in the Hamiltonian. That means that more change you have, smaller must be the gap, and more time step that you may use. So the number of projective measurement, the number of terms in those multiplication and this sum here has kind of an implicit dependency with the gap. So it's not clear if this goes always with 1 over the gap square at most, or if we can have a tighter bound. One technique that I want to introduce is the rewind procedure. So I said that every time one of your projective measurement fails, that you don't collapse into the ground state of your instantaneous Hamiltonian, you need to restart from scratch. So the rewind procedure allows you to actually going back and forth, so you don't have to restart your entire algorithm. So the main idea is, instead of using a full energy measurement, we will use a partial energy measurement that will, so that way you won't fully collapse into a state that is orthogonal to the state that you're looking for, in order to be able to kind of undo this projective measurement and recover either your starting state or your target state. So the idea is that on one step of the adiabatic schedule will be equivalent to any path that starts on this state and end up on this one. So you always start in the ground state of a given Hamiltonian, so the ground state of J minus 1, and you try to project into the ground state of the Hamiltonian J. So you can succeed with some probability, but you could fail and have a state that is orthogonal to the state that, that you actually wanted. So by trying to undo the method, you could with some probability recover your ground state, but you could also get a state that is, again, orthogonal to the state that you started in. And you can go back and forth on this graph until you reach your final state. Of course, it's not clear if that will give you any advantages, because you could think, well, maybe I will stay stuck in some back and forth here, or and it may cost more. And of course, if you're at your first step of your algorithm, well, you may be better to restart from scratch. But if you are at the end of your algorithm, that could be better to not have to restart from the very beginning. So we did some simulation, and it turns out that yes, a rewind procedure gives you some advantages. You use less resources by using rewind instead of restarting every time from scratch. So in this graph here, we have on the horizontal axis the total number of sites of the U-bar model. So recall that we're trying to find the ground state of the U-bar model, and so we have the total number of sites here. And the different shapes and colors represent the different shapes of your lattice. So for example, in black here, you have the 1D chain, and you have the ladder one in blue, so a depth 2 of the lattice, and you have depth 3 and depth 5. The only difference here with the red stars is the result that we got from exact diagonalization. So recall that we're finding all this value with tensor network method, which find an approximate solution. Just wanted to ensure that that we are finding a solution that we have a high confidence in the solution that we find. So we are actually in perfect agreement for small lattice size. So we're pretty confident in the result given by the tensor network method. On the y-axis, what we have is the gain from the rewind procedure. So it's the ratio of the cost of the method without rewind over the cost from the method with rewind. And what I mean by the cost, so recall that I said that the cost of the projective measurement will be 1 over the gap of your Hamiltonian, and this is basically the number of time you have to call the unitary to perform such a measurement. So the number of call of this unitary for the method without rewind over the rewind is what we define here as the gain. So whenever you have a value that is bigger than 1, that means that we have an advantage to use the rewind procedure. so that we will use in average less call to this unitary to reach the solution that we wanted. So this graph really takes into account the number of repetition, and for both cases we have independently optimized the number of time steps. So we really have kind of the optimal schedule in our framework for each case independently. So the graph is pretty scattered. But we still see that we seems to have an increase in the gain that you have from the rewind procedure when you grow your lattice size, or when actually you decrease the gap. So the gap is linked to the lattice size, but it's also linked to the shape. And so yeah, so we see that we have a gain from the rewind procedure. The next procedure I want to introduce is cubitization. So cubitization is some tricks that we will use to reduce the overall cost of the algorithm. So when we look at the TTS formula that I have here, it's obvious that the cost depends on 1 over the gap here, and that if we were to increase the gap, we will actually decrease the overall cost of the algorithm. So this is the main thing that helps us with cubitization. So cubitization will increase the gap of our system. Well, actually, okay, let's go into more detail here. So the cubitized unitary is given by something that looks like this. So it looks like the exponential of the arc cost over normalized Hamiltonian. So this unitary here lies in a bigger Hilbert space than our original Hamiltonian. And it's not actually a physical Hamiltonian. This is not any physical approach. So it's actually linked to a quantum walk. And what makes it particularly interesting is that we have an efficient way of implementing this operator, this unitary operator here. So the other thing is that it's modified the gap. So the gap of this walk operator is now given by the arc cost of the gap of our the normalized initial Hamiltonian. So again, it's not clear from this formula that this corresponds to an increase in the gap, but in our case, in the case that we study with the Hilbert model, it actually corresponds to an increase in the gap. So the dependency here, so the precision that we will need our energy measurement to be, will now be 1 over the arc cost of the initial normalized gap. So that will correspond to a decrease in the cost, but we have to be careful because now the probability of measuring depends on the eigenstate of your W operator and not on H anymore. So the eigenstate of this cubitized operator are linked in a null manner to the eigenstate of our original Hamiltonian Hg. Basically, it's up to anisometry, so we know how to recover Hg from the eigenstate of double Hg. But the gap, not the gap, sorry, the probability of measuring the ground state of, let's say, W1, given that you're in the ground state of W0, will be bounded by the probability of doing the same thing with the original Hamiltonian. So actually, it's not clear if we may need a higher density of measurement because the probability will now be lower. So again, it's not only from only from this formula, it's not clear if we'll have a gain or not. So we did some simulation, and again we have a great improvement from using cubitization. So here we represent again on the horizontal axis the total number of sites, and the different shapes represent the different lattice shape of the Hilbert model. So again, the 1D in black, ladder lattices in blue, the 3 for the green one, and the 5. So the gain is the ratio from not using the cubitization technique over it's the number of call that you do to the unitary that encode the exponential of your Hamiltonian over the number of call that you need to call your cubitized Hamiltonian, cubitized unitary. So we formulate this problem in terms of the call to those unitary, because this is actually the calls that you do in your quantum phase estimation. So you call the unitary to do your decomposition in the eigenbasis. And again, we have for intermediate lattice size, we have some gain that reach until 3 order of magnitude for this lattice shape, and it seems to increase with the total number of sites, and has some kind of dependency on the shape of the lattices. So this means that we have some kind of gain that seems to be better for bigger lattices, or lattices that has a smaller gap. But not only that, the other advantages, as I already mentioned, of using the cubitized unitary instead of the exponential of the Hamiltonian, is that you have an efficient and actually an exact implementation of the unitary. So in general, when you want to implement the exponential of an Hamiltonian, you will need to use some things like Trotter-Suzuki decomposition in order to approximate the unitary you're interested in. But in the case of the cubitized version, you actually have an exact implementation. So you don't have any error that comes from a decomposition. And the number of gates required to implement this cubitized version is roughly the same as the number of gates for one step of, let's say, a Suzuki-Trotter decomposition. So we can see that in most of the case, you will have a gain, or you will be roughly the same number of gates. So on the graph, what we have is on the x-axis, we have the total number of sites again, and the shapes. The different shapes and color represent the different shape of our Hamiltonian. The empty symbols represent the gate cost from when we use the exponential of the Hamiltonian, the non-cubitized version, and the filled one are the one where we use cubitization. So the y-axis is the t-depth. So when we are thinking about a fault-tolerant quantum computer, we're talking about a universal set of gates. So typically, Clifford plus t is what we use. And in that setting, the t-gate is considered as the more costly operation, because you will need tricks like magic state distillation or state injection to perform each one of those gates. So these are the ones that you need to minimize. So we have the depth in that, the t-depth in that sense. So you can see that when you use the cubitized version, that is, we have always something that is better than when we use the non-cubitized version. We have a gain actually that reach up to 7 order of magnitude in the number of gates. So again, all of this graph always include the number of repetition that you will need to do your algorithm. So this is kind of the overall cost when you take everything into account. Again, it's pretty scattered. So there's clearly an improvement, but what is this actual improvement is hard to define. So to have a sense of the scaling, I now have graphs in terms of the inverse of the minimal gap, because it's kind of more natural to express the adiabatical algorithm scaling in terms of the inverse of the minimal gap. So I mentioned that the adiabatical state preparation is upper bounded by 1 over the gap square. And well, the scaling of the algorithm is upper bounded by 1 over the gap square. And in the TPS formulation that we had, we only had one explicit dependency in 1 over the gap, but there was an idem part in the fidelity term and the number of steps that we will need. But in the cubitized version, again, this explicit dependency was now 1 over the arc cost of the gap instead of 1 over the gap itself. So when it's an increase in the gap, we can see that we will necessarily have a change in the scaling. So this is kind of what we wanted to illustrate it here. So in this graph, I have the 1D chain. And in this graph, I have the ladder lattices, so a Z2. And you can see the empty symbols are for the version without cubitization, and the filled symbol are the version with cubitization. In both cases, we clearly have a speed up from cubitization. And in the non-cubitized version, we can also see that the scaling seems better than 1 over the gap square, but we have to be careful here for multiple reasons. So first thing is, so this 1 over the gap square is an upper bound, and it's highly depends on the problem you're looking at. And here we even see that we seem to have a dependency not only on the gap, but in the lattice shape. So we expect we could expect the 1D case, that is a simpler problem, to have a better scaling than the latter version of it, but it doesn't seem to be the case. It could be because some of the improvement, some of the procedure we did had a better impact, a better improvement in those type of lattice. But again, it's kind of pretty scattered. So a clear trend. So the scaling cannot be assumed. Of course, come back again on this. The scaling of the cubitized version is now goes with 1 over the arc cost of the gap, but it's not the only reduction. Maybe there has we should use a bigger number of projective measurement, so we could increase the scaling here. But overall, we seem to have like a pretty neat improvement in the scaling. But it's almost impossible to distinguish between the gain that came from the method in general that we use, and the gain that is kind of specific to the system that we use, to the fact that we are simulating for the Hubert model only. So to conclude, we've presented and benchmarked a way to initialize the ground state of a quantum many-body system on a quantum computer that includes cubitization, classical optimization, interpolation, classically optimized interpolation, and a rewind procedure that gives an interesting gain, an interesting speed up that could be really critical for bigger systems than what we simulated here. The cubitization helps us because it offers a bigger gap. So I said that the gap decreases, but the gap increases, sorry, but the fidelity decreases. But clearly we have a better impact from the increase in the gap because we have a gain from the cubitization itself. The classically optimized interpolation helps us to kind of optimize the number of intermediate projective measurement that we need to do, so we can have a clever way of defining this. And the rewind procedure help us to kind of avoid having to restart from scratch, so we can have some gain that came from there too. Of course, we could add other interesting things that will help us to have even a better scaling. I'm thinking here about things like nonlinear interpolation. We already mentioned that we could have like a symmetry breaking field, maybe to increase the gap and make this adiabatical state preparation more efficient. But one question remains. What is the upper bound of this method? So of course, it is upper bound by the same thing as the usual discrete adiabatic state preparation, but you could probably have some more tighter bound on it. But this is something that is left unsolved by our research. So if we look at, for example, the time to solution, so the cost that we implemented for the method, even without rewind, this is quite hard to understand what is the scaling of this part, because we have kind of a high dependency on the model itself that is hidden here. So it's really hard to distinguish again between what is from the method from what is dependent on the system that we simulated here. So if you have any question, please feel free to ask.
Okay, so if there are any questions, you can either unmute yourself and ask them, or you could raise your virtual hand, and I will pick you accordingly. I think everybody has the ability to unmute. So maybe I have a question. So this might be somewhat misguided, but I mean, a big question sometimes in similar models, like not necessarily the Hubbard model, but some modification, is whether or not the system has a Fermi surface or Fermi arc. So could a similar algorithm, so basically could I take some modified Hubbard model or some Fermi Hubbard model or some kind of system that I don't know if it has a Fermi surface or Fermi arc, and apply a similar algorithm to concretely tell me, okay, the ground state has this Fermi surface ground state or Fermi arc ground state?
Maybe I'm less familiar with the condensed matter side. So when you say that there is this Fermi arc surface, you mean that basically it's non-degenerated, that you have a gap?
No, it will be gapless then, right? So if it's gapped, I mean, yeah, so I mean, if it's a Fermi arc, then it would only be gapped in certain places in a way. But if it's a Fermi surface, then it would be gapless. I mean,
if it's gapless, this method has no guarantee of succeeding. Yeah. So okay. This is the thing. Like if you you don't have a guaranteed gap, you have a vanishing gap or something like that. That could work in a sense. I mean, it's still, when you do projective measurement, you always have a kind of probability of, if you have some similarities with your previous like ground state and the ground state of your next one. But if you have like kind of but if it's not the case, well, you will never measure it.
Okay.
But you could luckily find it. It's just that you cannot bound the resource cost for such a method.
Okay, so I mean, and that's okay. So building off of that, I mean, like when I talk about a Fermi arc state, that sort of means that in some places, along the Fermi sphere, let's say homogeneous system, it might be gapped, and in gapless and in gapped, say. So could you detect the presence of a Fermi arc by looking at this system, looking at this algorithm, basically, because some parts would be gapped?
Or
is that sort of unexplored?
Honestly, I couldn't say.
Okay.
But yeah, if you have in like your evolution at some point something that a vanishing gap, I mean, you can't expect this method to work.
Yeah. Okay. Okay. Thank you. So Anna, any other questions? So maybe I'll wait 5 seconds in case someone wants to unmute themselves. Okay. So let's thank Jessica again.
Thank you. Thank you for the invitation.
Thank you for coming to give a talk.